Back to another video for my qualification. Today we are going to talk about vector integrals in integral theorems. And yes, this is my childhood board. It's a little old and a little broke, but I mean, we are all inside a little broke. So let's begin with integral theorems. There are quite enough integral theorems, so that's why this video is going to be in two parts. First, to know the integral theorems, we have to define what is a line integral. And a line integral is defined by this function. This means that we are going to integrate fx corresponding to dx. What does this mean? It means that x is our variable and dx is the derivative from our variable. If we have here a y, well, we can also use it from the point of view of x, but it's usually the same variable, so y. But for the integral theorems in the vector integrals, we need to know the curve, because we are talking about curves in our planes. Curve. And so we can use the curve in our integral. We have to have our curve in our parametric representation. And our parametric representation go like this. R from t is going to be equal to x t y t and c t. This is what the representation of a curve. And what this means, as I remember, is a plane. So it has the result of this go like this. This is how our curve will comportate in our plane, and this representation is useful in this kind of situation. What this line integral means is that we are going from the point A to our point B in curves, okay? This is how our system will comport. This point here is C. So the line integral means that we integrate A to get B from C. This also works in this kind of situation where A and B are in the same point. Okay? So a line integral, how we get the integral from this? Well, is with this formula. Hold on. This is going to be equal to here we are going to get our function times our curve, the dot product of the derivative of a curve in respect to t. This is the formula we're going to use. Okay, let's see a quick example. We have our function. We have our curve. And we have t. Okay. First, we have to substitute the values of x and y. So, this is y, this is x, minus sine of t, minus cosine of t, sine of t. Okay. And then we need to have the derivative of this, but easy. Our prime is t is the derivative of t, so derivative of cosine is minus sine, sorry, cosine of t. And remember our formula. It's a dot product, so we have to take the dot product of this and this. We get this is for integral, and we just have to substitute the values, and this is going to transform into our answer, which is the 4 part of p minus 0 minus one third, and this gets this is our answer of linear integrate. And now that we explain a little what is a linear integrate and we see an example, we are going to pass to our theorem, which means there are less problems and more theory, so it must be more easier to catch. Let me just take rid of this. Now is path independent. And when our linear integral is independent, well, when we have a linear integral, with constant functions in some domain, which is going to be t, and these constant functions are the gradient of or any function, then and only then our integral is going to be a path independent. So what does this mean? Well, this is also explained with our little example, quick sample. It doesn't have any numbers, so watch out. No, calm down. Sorry, calm down. So our integral is going to be the same, but f1 of x, f2 of y, and f3 of z. Remember, is when we have a gradient. Remember, gradient is the symbol, and it's represented by the partial derivative of our functions. So this is going to transform into this, or partial derivatives. This is our gradients of every function, but we have to have it in the domain of time. So this transform into this. We have our partial derivatives of every function in the domain of t, and we can just resume this into this little integral. Is b of this. Now this is the equal of having this. And now we just have to substitute the values of the integral. That goes like this. And if we resume this, we obtain, I'm going to, that oriented rate goes from f of b minus f of a. When we get this, it's going to represent our path independence in the domain of D with constant functions. But our next theorem about path independence says that when A and B, or remember those are our points in our curve, are 0, then our function or linear integral is going to have path independence. But when A and B are going to have the value of 0, well, this is represented by this. A and B are going to have the value of 0 when the sums of A and B, but the sum of A and B but in different directions are 0. Oh, okay? Am I explaining myself? The sum of A and B, but when both of them go in different directions, must be 0. So if A is 1, B must have minus 1 because go in the different direction, and 1 minus 1 is 0. This is when the parts have independence in the domain. This is our theorem of path independence, and we are going to see a little subject to understand the next theorems because they use double integrals, and I'm going to explain yourself. I'm going to explain you what is a double integral. with double integral. As the name says, a double integral is just an integral that is double. So this is one integral, this is a double integral. Easy as that. This means that our function is going to be integrated twice. But as we're going to integrate twice, we need to have two values and two derivatives. From each value of we can do a double integral. How we get this in a plane? Well, this just means that we have to create paths that go parallel to y and parallel to x. This is where our double integral works. I have to say it is easier to work in a board than in a window. So we have that fx is going to be continuous in our curve, but this time is not just a curve. The double integral means that our object is bounded by many finitely curves. So it's not only a curve, like we see in the last example. There are many curves that compose our domain. So this means this transforms this into this. But this is the general formula, and we have to get our integral. So this becomes this. The integrate of the integrate. The integrate of the integrate of our function. Of dx of dy. This is general, you can make it free from dy and then dx is not important. You have to, in a double integral, you have to first integrate this part, and the result of this you have to integrate again, but with the other values that the problem gives you. And this means, I'm going to do this is not really important, that if we want to get this, it means that we are going to work over here. This is for our integrate in x, and this is for our integrate in y. The double integral serves us to calculate the volume of a or figure, the density of the figure, you just have to be a little creative where do you want to use the double integral. But the double integral have a little problem. It's a little complicated, okay? So it's a lot of calculus, and to solve this, we have our next theorem, the Green's theorem. So Green's theorem, what does Green's theorem tell us? Well, it tells us that we have R, which is a closed boundary that exists in our X and Y plane, and in R exists our boundary C that is component by finitely many curves, and we have our function f1 and f2 who are constant partial derivatives and they exist in any part of the domain R, okay? F1, F2 exist all over here. And the Green theorems tell us that our double integral of or partial derivative of f1 minus f2 transform into this. They stop being those partial derivatives, they transform into the sum of the derivatives of x and y of our function f1 and f2. The Green theorem tells us that they are no longer existing anywhere of R, okay? They exist inside C, as you can see. But C can be anywhere of R, so they are still existing in R, but not everywhere they want. And in this theorem, we have to integrate in a way that R is always on the left of our integrand. Okay, that's what the Green theorem tells us. As you can see, it's easy. It's not very difficult, and it actually is all of the Green theorem. And now we are going to go to the tangent plane and the surface normal. This is another theorem, and it's quite quickly actually. What does this mean? Well, it means that we have a surface S. S given by this. And this is equal to this is our surface, and it will have a continuous RUV given by this. And is going to be equal to RU times RV, and the result of this has to be different from 0. Okay? And all of this just means that if our conditions are correct, get accomplished, then S we have in every point of the surface a tangent plane, and that tangent plane will go to any point of the surface. I need to make a draw, so I'm going to erase this. If our function are, if RU, RV are continuous, and we have our surface defined by this, then it means that this is going to be our surface. This is our surface, and here we're going to have our plane, or tangent plane, and our tangent plane are going to be straight by RU and RV. This is P, this is point, and this is N. This is going to be our tangent plane, okay? But it's going to go to any part of our surface. This tangent plane could be here, or here, as long as we get our condition accomplished. So this is our unit normal vector given by this. And our N is going to be get by this. This is how we get N, and 1 over the absolute value of N are going to give us N, or tangent plane. This tangent plane, this function, this theorem, is going to be used to get our surface integrals, or triple integrals, our stroke integrals, and another integral that we're going to see in the next video. So I'm not going to say goodbye, because I will see you in actually a week from now. So, you know, like, share, I don't know. So I hope you like this part of this video, and I hope it has the correct length. So see you in a week.